Hello and welcome to Paraag Tutoring. Today we would like to start with the FPGA design tutorial. Now before we move on to FPGA design flow tutorial, we would like to first of all let us be comfortable with what do you mean by an FPGA. So generally speaking, the integrated circuits are manufactured via two means. Now one way of manufacturing speaks about the programmable type of logics, which is programmable logic devices, right? And the other way is to get around with application specific ICs, like application specific ICs. Now when we speak about application specific ICs, these are generally the ICs which are designed in the fabrication labs, so they do not have they could not be designed in the field, right? We cannot design it in our laboratories or something like that. They have to be designed in the specialized atmosphere which are which is desired to make them comfortable. However, in case of programmable logic devices, they are the devices which are already available in the form of ICs, right? So they are already ICs now, so they are pre-prepared, that it is something like you already have some sort of uh, a picture which is already ready to be tailored, something like that. So already available in the form of ICs, and they just needs to be programmed. So programmed as per the new application. So they can be programmed as per the new application. If the application changes, then they can be reprogrammed corresponding to the newer application, something like that. So this kind of programmability in hardware was the result of uh, specialized efforts which took place something around 70s to 80s, in fact in 80s, 70s to 80s, 1980s, where we have got some PLA, PL and ROMs. So these are the basic initiations of programmable hardware. These are all programmable hardware initiatives. These are the things which has break this view of hardware being constant or hardware being non-programmable. So this has break the jinx of hardware being non-programmable. From here, which is programmable logic array, programmable array logics, and programmable read-only memories. They actually contained uh, programmable or fixed and or arrays. So they are either programmable or fixed. They are either programmable or fixed, something like that. If some in some cases they are having programmable and fixed or, in some other cases they have programmable fixed and programmable or, and some at some other times they had programmable and programmable or. So in this way they used to generate some sort of SOP and the POS functions which are which through which you can be able to program any combination circuit. Now this is basically the beginning of programmability in hardware, and this has this has gone ahead, and this has been applied initially for the simple programmable logic circuits. The At that point of time, the ICs which were visible, they were belonging to the domain of SSI, MSI, medium scale integration, and NSI domains. However, as we have gone ahead with the manufacturing technologies, and when as we have approached to VLSI and ULSI technologies, so corresponding to these technologies, as we went ahead with the application specific ICs, same is the case with programmable ICs also. So corresponding to this VLSI and ULSI technology, we went all ahead for the programmable logic devices, and these devices were called as CPLDs. So before CPLDs, we used to have for LSI specifically, we used to go for SPLDs, that is simple programmable logic devices, which have incorporated. Now these three have incorporated only combinational circuits. Usually we used to design programmable combinational logic circuits using these uh, these devices. However, we went for combinational plus sequential by making use of sort of simple PLDs or SPLDs. And later on, when we went for complex IC designing, which are in the range of VLSI and ULSI, that time we have designed, in fact, the industries have designed CPLDs and FPGAs. So this is where the term came from. So CPLDs and FPGAs are CPLD are the programmable logic devices, PLDs, which are highly complex in nature, of the order of VLSI and ULSI. That is, they may be having about 1 million devices within them, and they can be programmable. So definitely the complexity level of VLSI and ULSI level of ICs can be programmed now very easily. And the most important point is that now let us try to expand the way we try to imagine about FPGA. So FPGA is a acronym for field programmable gate arrays. you know Gate arrays. So if you expand this acronym, then we can say that it is an array of gates which are programmable in field. Now when we say they are programmable in field, means they can be programmed in the lab. So we can have a big array of gates of the complexities of VLSI and ULSI, which can be programmed in field, that is that is in the lab. So we don't have to go to the fabrication lab for programming or for designing these ICs. So suppose today you would like to say that, oh, you'll be requiring this sort of uh, processor for your design requirements, then you can end up in processor design within 10 days, or who knows, before than that. If you know exactly what you want, then you can program your FPGA as per your desired requirements, and then you can maybe you can be able to get it through within few days, maybe 8 days or 10 days. So that is the value addition which has been done by FPGA devices. And today we would like to learn that the design flow means nothing but today we would like to learn the set of steps which we'll have to encounter in order to design any hardware in terms of FPGA. So today we'll see all the set of steps. Now we'll be basically dealing with two sort of design flows. One is the generic design flow. This is the beginning generic design flow, in which we are trying to design some we are trying to see some design flow which is generally incurred in all the FPGA, all the EDA tools. So EDA tool vendors. So most prominent EDA tool vendors, which sells their tools on Windows platform as well as Linux, but they are more popular on Windows. They are from Xilinx and Altera. These are the two most popular FPGA vendors, EDA tool vendors. EDA stands for Electronic Design Automation, and out of which in India particularly, as far as I have seen, most popular is Xilinx. Although these are popular for Windows operating system, and I mean, I'm not saying that these are only two. There are some other ones also, but these are the two most popular vendors. Apart from this, there are some vendors which are hugely popular in the industry. I'm speaking about academia when I speak about Xilinx and Altera, but in the industry, there are some more vendors which are hugely popular, and they are more accurate and they are more precise apart than these one. They are Synopsys, and I mean there are variety of those Synopsys, Cadence, and there are so many such vendors which are more hugely popular in the Linux operating system or Unix operating system. However, my talk is more focused on Xilinx and Xilinx FPGAs. So I would like to discuss the the processing steps, the way we process any circuit within an FPGA to be designed onto an FPGA using Xilinx. So initially, let's start with FPGA design flow in generic sense, and then I'll focus more on to specifically targeted for Xilinx. So as I'm using Xilinx since long time, so I'll be focusing more on to Xilinx. So this is all about the today's presentation outline. Now let us start with the generic flow. Now FPGA design flow every time starts with the design specifications. Now it is nothing common for designing anything. Whatever you want to design, whether you are in academia or in the industry, you naturally have to start with specification. Without specification, nothing comes true. For example, if you are asked your names, and then you will be recognized by your name. So your name is a specification of you. You are recognized by that name. So design specification is the basic building point of designing anything, whatever you want to design. So design specification, it starts. Now it's a textual description, right? So generally, design specification are the step of design specification uh, ends with a view of forming a clear-cut description of the design in the form of a block. So generally, designers usually do the block diagram description after they do with design specification. So next is block diagram. Now in the block diagram, we generally try to count for how many number of inputs and how many number of outputs which are available for the design. Now after this block diagram stage, usually it is not shown over here, but it's pretty obvious. Without the block diagram, we cannot go for design entry. In fact, sometimes people say that block diagram design is also a kind of design entry. However, we can draw it on the paper also. There is no issue in that. And then after doing this, we'll generally go for design entry. Now design entry here can be done depending on your choice of the particular syllabus, choice of a particular client, depending on whatsoever it is. So it can be done in two ways. One is using VHDL and other is using Verilog HDL. So here comes the use of HDLs. I am planning to take one more session separately for the importance of HDLs in the design of digital circuits. So in that session, I will discuss more in details about why do we go for HDLs and what are the roles which the HDL plays in designing digital circuits, and what all was there before HDL was not initiated. So I mean that's a separate story, but in this case we'll focus more onto basic hardware description language, or another language is Verilog HDL. So these are the two most popular HDLs, and then we are having a choice at the time of making design entry, that whether we can describe our design, that is whether how we are able to convert our block diagram description in the form of a HDL description by using design entry. Now design entry is followed by RTL model. RTL model is nothing but the way you write down your code so that it can infer the same hardware what you are looking for. Now to brief you in short, HDL is nothing but another language. Now the language is pretty different than the normal higher level language, in the sense that HDLs are used to describe the hardware. So they are written in by keeping in view the hardware intent in mind. So hardware intent is there in the background, and keeping in view the hardware intent, they are designed. So therefore they are, as they are, their name suggests, they are hardware description languages. So they are trying to describe the hardware. So apart from the simulation, which a typical language is capable of doing, they are also inferring the hardware. So apart from simulation, they also design, or they also infer. Rather than we say design, they also infer the hardware. And when we say hardware, then definitely it's a digital hardware, no doubt about it. Without having any other sense, it's only a digital hardware. So this is how we'll try to make a RTL model. For that, RTL stands for register transfer logic. So this is the way we'll design a RTL model, register transfer logic. So this is the way we'll design a RTL model, and using this RTL model, now there is a separate story behind it, how we can be able to design different type of RTL models. the way we are able to describe the HDLs. So that corresponds to that. So we are not going to the detail of RTL model right now. So all what we can say over here is that whenever we make a design entry in the form of an HDL, RTL model will suggest that what sort of path which you have to take in order to go ahead uh, with the FPGA design flow. Now after this we'll go for functional simulation. Now this is for the first time we'll try to verify the functionality of the design. So in this functional simulation we'll try to verify the functionality of the design. Functionality. Verify the functionality of the design. Now in this case, while verifying the functionality, we sometimes also name it as a zero delay simulation. Now why do we say about zero delay simulation? Because as of now, while doing this simulation, we have not taken into account any of the target devices which we are targeting for. For example, suppose we are trying to target for one particular FPGA. So as of now, we have not taken into account any inclusion of that FPGA. I mean any hardware resources of that FPGA, and therefore it is as if we are trying to simulate this design on paper, and we say that on paper design is nothing but a simple simulation, as if we are trying to solve an equation. So on paper, so there is nothing, no hardware intent is present. So therefore that is called as functional simulation or zero delay simulation. So that after this RTL model, the first step is to perform the zero delay simulation or functional verification of the design. Now sometimes we can do this functional verification by directly imposing the input vectors onto the design and trying to test the output. However, there are some more alternatives which are more profitable, in the sense that sometimes we may also go for writing a test bench for simulating the functionality of the design. Now test bench in this case is nothing but it is another HDL model, but in this case this model is particularly targeted for testing the existing design. So it's not a design in itself, it is just a testing unit, testing entity which is used to test an already existing design. So it doesn't have any ports, however it does have some hardware, some wires to connect them to the ports of the design, so that the design can be very well tested. And now this is the end of the story for testing. Once we test a particular design in proper ways, then definitely we will make sure that the design is matching the requirements, the desired requirements of design specification. So if we say that it matches the desired outputs, then we'll end over here as far as the functional simulation is concerned, and then we'll go ahead for actual designing the hardware. Now in this case, now as I have said that HDL is meant for simulation which we already performed plus the hardware intent. That is, now we are trying to realize it in the form of a hardware. Now when we realize that, then we'll have to choose a particular target device corresponding to the same, and this particular target device comes from the vendor. For example, if it's a Xilinx tool, then that particular device FPGAs belong are Xilinx FPGAs. So they may be different families, they may belong to different families, they may belong to Spartan, they may belong to Vertex, whatsoever may be the case. So these are the different FPGAs which can be chosen at this point of time. So synthesis is nothing but the actual synthesis of the hardware corresponding to the target technology by making use of resources of the target technology. And therefore now at the same time, so we'll have to provide some HDL file onto this synthesis tool, so that it converts that HDL file to some gate level description which we can use for the further processes. So it is nothing but the conversion of HDL into the gate level description corresponding to it. And this can be done by using the target library cells. So there are different library cells which are available for from the FPGA resource, and it will choose that particular FPGA resource corresponding to the code which you have written. Now, uh, there may be different possibilities over here. For example, suppose we have written the code for simulation. Sometimes the constructs which we choose for simulation of hardware, they may not be suitable for synthesis. Therefore, in this case, sometimes we may have to go for choosing some different constructs which are synthesizable. At the same time, they are simulation results are also good. So, I mean, there is something called a simulation and synthesis mismatch, which we will have to avoid at this point of time. So, sometimes it may so happen that while simulating, we do not we disregard the actual inference of the hardware from a particular HDL code. For example, if you use if else or a case statement, it doesn't make any difference as far as the simulation is concerned, but sometimes it makes a bit of a difference when we'll go for synthesis. So that's the reason why while doing synthesis, we may have to see that whatever we have written on the code, what kind of hardware we are trying to generate out of that, and that comes with practice. So this is one thing which we try to do with synthesis. Another thing which we'll have to focus on at this point of time is that now we'll have to choose whether the the design constraints which we may have to apply for this design is corresponding to area or speed. Now over here, as far as the designing of VLSI integrated circuits are concerned, we can have two options to optimize the design of an integrated circuit. We may have to optimize that VLSI circuit corresponding to area, and when we say area, then we have to definitely go for minimizing the area. Second optimization is speed, that is we'll try to work out at maximum speeds as far as possible. So that's and the third realization, which is very much hot in today's world, it is power optimization. And as far as power is concerned, we all try to work it around for low power devices, and the power has to be as low as possible. So these are the three design criteria on the basis of which we are trying to optimize the integrated circuit. Now, out of these criteria, unfortunately, there is a trade-off between the three. I mean, right now our synthesis tool has got these two prominent areas, area and speed. So there exists a trade-off between the two. Trade-off in the sense, uh, when we'll try to optimize for area, unfortunately the speed decreases, and when we try to optimize the speed, the area increases. So this trade-off is a very difficult one, and that's the reason why the synthesis tool asks the designer whether the designer wants to optimize this design corresponding to area or corresponding to speed. Now there are different available options over here. For example, if you are designing a complex hardware, see, if you are designing a simple digital hardware corresponding to your academic requirements, it doesn't make much difference whether you optimize for area or speed, doesn't make much difference. But if you are designing a complex hardware which is just fit for that particular FPGA or CPLD, that time it makes a big difference. So at that time we'll have to really see that whether our hardware and our chosen FPGA has got some matching characteristics or not. For example, our hardware which we are trying to design be able to fit better in an FPGA, or not able to fit. I mean, that's the area constraint. That's where we have to apply a area constraint, and at the same time we have to also see that whether we are desiring the speed of operation. That is, we want that the clock speed of the particular hardware design must work at that particular frequency. Let's say 500 gigahertz, or I'm sorry, 500 megahertz. And if your design is trying to achieve, let's say 496, or I'm sorry, it's 450 or 460 megahertz, then definitely uh, we'll have to make our design pull towards 500. So that time we'll have to apply speed constraint. So I mean, it's something like this. So it all depends on the real life situations, what the situation demands at that point of time, and accordingly choose one of the particular design constraints. Then let's go ahead. Suppose you have chosen by default the area constraint is chosen by the synthesis tools, and then we'll go ahead with the next model. Now next is the gate level model. So actually speaking, synthesis converts your RTL model, which was written in HDL, into another gate level model Now this gate level model is set to be uh, generating a file which is known as electronic design interchange format file. So that is EDF file, EDIF file. Now in this file we have taken into account all the type of logic gates, and in fact all the type of devices which we resources of the FPGAs which we have actually accounted for. So it is converted into a form in the form of a file which is having a gate level model into it. Then after this we'll go for further mapping and translation, that is the implementation step. Now sometimes beforehand, although we do not generally perform this and this in case of academics. However, it is always better to perform one more simulation after synthesis, which is called as post-synthesis simulation, and this is also called as gate level simulation. For the simple reason being, at this point of time, now the design also incorporates the propagation delays, which are gate delays, along with the design. So therefore we may have to perform the gate level simulation by making use of the same test bench which we have used earlier, and I mean we'll have to match with the design specification whether the design is meeting with the requirements or not. There are several factors which decides whether the design meets with the requirement or not over here. So that's the gate level simulation, and then once we perform that, then we'll go ahead with the last step of this design process, in which we call it as an implementation. So the last step is implementation, and we over here, I mean sometimes it is also called as physical design, and it is nothing but we are trying to incorporate the design as if we are trying to incorporate the design onto the physical device. That is, I mean if you have heard about PCB, so it's similar to a design of a PCB layout. So layouting stage we can say, this is the stage of implementation. So here in this case we are trying to map our design and translate it onto the device architecture. So we are trying to see that how does it route, how the design will route, where the components of the design will go, which are the components of an FPGA which are to be taken, how they are spread, how they are connected together, all these things the the tool does. I mean from synthesis onwards, everything is tool dependent. So beforehand, before this, uh, the designer control is there, but after this the designer actually lineates the control to the tool. So beyond synthesis, everything is tool dependent. In fact, why beyond synthesis? In fact, from synthesis point onwards, everything is tool dependent. So everything depends on the tool. Whatever tool does, we'll have to observe, and accordingly, if required, we'll have to change our design. Else we'll have to change our constraints. So there are several things which I have to do while doing that. So so everything is tool dependent. So all these things, mapping and translation, everything is done by the tool. So it maps gate level model to the device architecture. Further than that, it goes for placing and routing the design, placing the design in the device while optimizing it for speed and area. Now here also the two things which we have taken into account for synthesis will take place here also in mapping and translation and placing and routing. That is, the choice of design constraint which we have chosen for at the time of synthesis, for example area, will be repeated over here. So again the design has been made to optimize for area. And in this case now, we'll have to also account for interconnections here, because now the design is there onto the real-time FPGA, as if it is mapped onto the real-time FPGA and placed and routed. And in this case, therefore, it's very important to see that whether the design is able to fit into the FPGA or not. Now the fitting over here is different than the fitting at the time of synthesis. Synthesis will not actually visualize the design placed into the, 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 the FPGA. It just try to visualize the design by taking the resources which are desired for the designing of a circuit onto FPGA. So that's the difference, right? So this the placing and routing is slightly different than the synthesis in this regard, because in this case now we are trying to visualize that as if we have placed the design onto the FPGA, then how do the design behave. And sometimes in the industry we'll also perform some simulation which is called as timing simulation over here, which incorporates now gate delays as well as the interconnect delays, because now there are interconnects which are also uh, there along with the gate delays, and therefore we'll perform timing simulation beyond that. And now that's an optional case. This gate table simulation and timing simulation is optional when we'll go for academics. However, in the industry, it's pretty mandatory while doing uh, product designing, right? Now, next is after doing this, then we'll go for programming the file generation. Now, in this case, after the result of implementation, we generally get one file which is called as bitstream file, and sometimes it is also called as bit file. So it is similar to the hex file which we generally get in microcontroller programming, similar to that, because FPGA is a digital device, so digital device needs some digital data for it to be programmed, and therefore we'll have to convert whatever file which we have got from the gate level model to some bit file which is used to program a particular FPGA here. So this is the program file generation which takes place as an outcome of placing and routing, that is implementation. And once we generate this file, the next task is to download that file onto FPGA, and that's the final step. So this is the way we'll try to download our design onto FPGA. Now this is all about the generic design flow which we'll have to incorporate for every EDA tool. Now let us be specific for Xilinx now. The next step is to discuss the same design flow for Xilinx ISE, Integrated Software Environment. Now in this case, we start with the same set of steps. For example, entering your design and selecting the hierarchy. Then that is the design entry in the form of an HDL. Next, it follows with functional simulation of the design. Then it is followed with adding design constraints. So we'll generally add different type of design constraints. After this simulation, in order to go for synthesis, and after this we'll perform the synthesis and optimize our design corresponding to the constraint which you have chosen over here. So same set of steps will follow in case of Xilinx ISE, Integrated Software Environment. And then it is followed by evaluating the design size and performance. So as I have said that if the design is big enough which cannot be able to fit in an FPGA, we'll have to optimize for area, so that we'll have to minimize the area. And then if you are minimizing the area, we'll have to compromise on speed. Similarly, if you want your design to operate on a particular frequency and you are lagging that frequency, you are lagging behind that frequency, then definitely we'll have to go for optimizing the speed. So these are the two optimizations which are possible. So after doing this synthesis stage, then we'll go for placing and routing your design. That is the implementation stage of the design. So in this case, we'll try to implement the design. At the same time, we can also perform the timing simulation of the design. And in the industry, as I have told that industry also does static timing analysis, so as to ensure that whether the design meets the design specifications or not. So after doing this, then finally we'll go for the bitstream file generation. That is the .bit file which is generated as a result of implementation. We'll download that that particular device bitstream file onto FPGA, and then we'll also create PROM and JTAG file. So this is the way we can be able to program a particular FPGA by following these steps. So I mean, we can say that these steps which the Xilinx obey, they are not pretty different than the generic steps. So all the generic steps are taken care of by Xilinx too. Now here we'll have a quick review of whatever broad review of the steps which you have performed. Here design entry, we have started with design entry. Now design entry has got two alternatives. One is performing the HDL coding for synthesis as the target. So we can have design entry in the form of an HDL code, and as it is relevant that there are two types of HDLs which we use over here. One is VHDL and other is Verilog HDL. So these are the two possibilities of using HDLs. and the second possibility is using cores. Now this possibility is basically taken for quick development. For example, let's say if you want to have if you want to use some sort of memory, and for using that memory, there are two options. One option is you already have that memory on your as a FPGA resource, and you try to instantiate that memory from that FPGA resource. Other option stems from designing that memory from the scratch. So right now, today is the world of system on chip design, and in this SoC design there are multiple cores which are already available, and we are trying to integrate those cores together so that the design turnaround will be minimized. And that's the reason why we'll generally prefer, I mean, lot of industries, they usually prefer the design entry using the cores which are existing. Some of them are free, some of them are costly. They are available on the websites of different industries. So these are the two options. The next is followed by a functional simulation of synthesizable HDL code. Now there is a difference between the code which is synthesizable and the code which is not synthesizable. For example, the code which we have written for a design is definitely a synthesizable code, whereas the code which we write for a test bench, for example, which is used to test a design, that comes in non-synthesizable, because we are not going to design a hardware for that. So that is a non-synthesizable code. So here we perform functional simulation. Now there are more than that. There are third-party tools which are also available along with the Xilinx ISE. Now one of the most important tool is from Enter Graphics. This is from Enter Graphics, and this tool is basically known as Model Sim. So another very good efficient tool. Now remember that this is only a simulation tool. We cannot be able to synthesize our hardware using this, but it is the most efficient simulation tool which is there on the Windows platform. Maybe it is available on Linux platform also, or Unix platform also. So that's another third-party tool which is used for functionally verifying the functionality of the design or simulation of the design. Then it is succeeded by the design synthesis. The Xilinx Project Navigator is used for this synthesis, and then it is followed by design implementation. And we usually go for design manager for implementing the design. Now the core steps which we generally go about in these design flow is they are listed here. That first is again the option of VHDL Verilog. Second is simulating the design functionality. Third is the synthesis. Now this is optional in case of academics. In academia, this and this simulation is optional. So sometimes we may or we may not go for these simulations. Post synthesis simulation. Then we'll go for implementation. That is mapping the design, placement and routing the design. Then we'll go for timing simulation, and then lastly we'll try to program the device onto the FPGA. So that's all for now. Today we have discussed some slight, brief review of the basic steps which we generally follow in order to design an FPGA. Now for further inquiries you can contact me on my email ID, and at the same time I am also available on WhatsApp, so you can very well touch me on WhatsApp also. uh, I'm also available on Skype, so my Skype ID is this one, so you can also contact me on this Skype ID. So I'm available on this Skype ID also. Okay, so that's all for now. Thank you for watching.